Hi, I'm Professor David Farina. In today's lecture, we're going to be discussing light and matter and how it is connected to the inner workings of our cosmos. Specifically, we're going to be talking about thermal radiation. Let's get started. So, the first and a very important term that I'd like to discuss with you today is blackbody radiation. What is blackbody radiation? Well, blackbody radiation is basically the energy that's being left out of anything that has a temperature to it. A perfect blackbody emitter would not reflect any radiation. It would absorb everything. And it would also emit in all wavelengths as well. That's all the way from the radio side of the spectrum all the way up to the gamma rays part of the spectrum. So it's a weird name, but all it means is it's the complete emission or complete absorption of all radiation types. You should click those animations at the bottom, and I'll put them in the links below if you're interested in working with them. These blackbody radiation links are going to be very helpful for you in your understanding of both blackbody radiation and its connection to astronomy. So when we're discussing things in astronomy, we need to consider the Kelvin temperature scale. So the Kelvin temperature scale is the scale that starts at absolute zero. It's in every single other way, like the Celsius scale. So you'll notice that, for instance, on the Celsius scale here, we have zero starting point, is the freezing point of water, and 100 degrees Celsius is the boiling point of water. Notice that on the Kelvin scale, which starts at absolute zero, where all thermal motion stops, there is still a 100 Kelvin difference between those two values that line up identically with the Celsius scale. So they are the same incremental differences between each step on the Kelvin scale and the Celsius scale. It's just that the beginning point, the 0 point, is different. Once again, Celsius is zero, the melting or freezing point of water, whereas Kelvin is all thermal motion stops. Now in Fahrenheit, since we're here in the US, this temperature would be negative 459 degrees Fahrenheit. Of course, 32 degrees Fahrenheit is the melting or freezing point of liquid water, and then the boiling point of water is 212 degrees Fahrenheit. Technically, there's no top to any of these scales. They could go on forever. But hydrogen fusion, that would be happening in something like a star, would be happening at these temperatures on all of these scales. So 10 million degrees Celsius or 18 million degrees Fahrenheit is that temperature for hydrogen fusion to occur. Now, there are two main laws of blackbody radiation. The first one is that the hotter an object is, the more energy it emits. And once again, I would like you to click on this link on the PhET simulation to learn more about how this works. But here's the equation. So the equation is stating that the amount of flux, the amount of energy coming out of 1 square meter over 1 second, is going to be related to something which is called the Stefan-Boltzmann constant. That's that funky little symbol here. Times temperature to the 4th power. So as you can see, temperature being to the 4th power is going to control this entire equation. So if temperature goes up or goes down, the amount of flux or energy coming out of a particular body, let's say a star or a planet, is going to increase or decrease dramatically. The second law is called Wien's law. And Wien, spelled W-I-E-N, Wien's law states that the peak of a blackbody spectrum shifts towards shorter wavelength when temperatures increase. Remember, short wavelengths are also high energy, more towards the gamma side of the spectrum. And as you can see in this little diagram here, we start off with temperatures that are 60 Kelvin, a dark nebula, and we're seeing it in the radio spectrum here because the peak is in the radio spectrum because it is a very, very cold object. Now, as we move to warmer objects, like, for instance, an emission nebula, now we've got some star forming occurring here, and we see it in the infrared part of the spectrum. Starburst. Planets could also be found with the infrared parts of the spectrum as well. Here's a star itself, like our sun. This is the sun, and you'll notice it's in the visible spectrum. Of course it is, because that's what we see. As Earthlings, we are adapted towards seeing things from our sun, which happens to glow in the green part of the spectrum. But because that's where the peak is, we also get to see the red and the blue side. R, G, and B together make white light. The sun is actually more of a white color. If you were in outer space, that's how you would see it. There is a filtering process that's happening as that light's passing into the Earth's atmosphere, giving it its yellow hue. Finally, as we get to the highest energies here, we've got 60,000 Kelvin, and notice that the peak is now off into the ultraviolet parts of the spectrum. So Wien's law, here the equation is giving us the wavelength, that's that symbol. Okay, so we've got lambda, which is wavelength, max, the peaks here, this part on every one of these diagrams, the peak is equal to 3 million nanometers divided by the temperature in Kelvin. So the smaller that this temperature gets, the longer the wavelength gets. The higher this temperature gets, the shorter this wavelength gets. And that's how we end up with Wien's law. I hope our lecture today on thermal radiation was helpful and that you learned something. If you did, please like and subscribe at the bottom.